Exercise 7. So we are given two groups here, G and N. G consists of all functions tau a b, where a and b are real numbers and a is non-zero, where the functions are defined like this. Tau a b maps any real number x onto ax plus b. B is the set of all real numbers, so that the function is defined like this. And N is the subset of G consisting of those tau a b where a is equal to the real number 1. We have to prove two things. First, we have to show that N is a normal subgroup of G, and that is why this quotient G by N makes sense. And this G by N is isomorphic to the group of all non-zero real numbers under multiplication. We in fact already have come across these functions in a previous exercise. So we already know that this G is a group. And by the way, what is the binary operation in G? The operation in G is composition of functions. And in fact, in that exercise where we came across these tau a b's for the first time, the one after that, the next exercise shows that this N is actually a normal subgroup of G. So this part we don't have to do, we will just refer to that exercise. The last part we have to show, okay, that isomorphism we have to show. So let us see the solution. So we start the solution by mentioning that we already know N is a normal subgroup of G, and it follows from this exercise. Exercise 23 of section 2.5 shows, which we have already solved, that N is a normal subgroup of G. Okay, so now we will show this isomorphism. So for that, it will be better to denote this second group by some symbol. Let G bar denote the group of all non-zero real numbers. Under multiplication. Okay. We are now going to define a function from G into G bar. Define phi from G into G bar by phi of any element of G will look like this, tau a b, and it's mapped by phi onto A. A word about this notation. See, previously when we saw these symbols for the first time, there in that in the solution to that exercise, we decided to use this notation instead of this one, which is somewhat confusing because of this reason. If someone writes tau 2, 3, then we understand this is 2 and 3. It's not 23 because the notation requires two real numbers. So there is no confusion about this. There is no problem with this notation. However, if for example one writes 2, 3, 6 or say 2, 3, 7. What am I supposed to understand from this? Does it mean that it is tau 23, 7, where 23 is A and 7 is B, or does it mean tau 2, 37, where A is 2 and B is 37? So that type of confusion can arise. So that is why we already decided there to use a comma to distinguish between A and B. So we are just simply continuing, we simply continue to use this new notation without mentioning anything else, since we are anyway referring to those exercises. So this is our function which maps this mapping tau A comma B onto A. Now note that, in fact let's just write that. Note that since for every tau A comma B belonging to G, A is not equal to 0, because that type of functions only we are considering where A is a non-zero real number. So we have phi of tau A comma B belonging to G bar. A is a non-zero real number, so it belongs to G bar, which is the group of non-zero real numbers. So the outputs are in fact in G bar. Okay, that much we have, but still we have to show that equal inputs produce equal outputs. In order to claim that the function we have defined phi is actually well defined, then only we can work with it. So next, let belong to G such that they are equal. We have to prove that their phi images are also equal. Now what does it mean for these two things to be equal? Since they are after all real valued functions of a real variable, so as functions they are equal, they are one and the same. Okay, so this implies Ax plus B, which is this, is equal to tau C comma dx, which is Cx plus D for all real numbers x. We use these since in the exercise itself we are denoting the set of real numbers by V. It's a little unnatural, but still we use that itself. Okay, so now we put special values of x to simplify the situation and to say something about A, B, C and D. Then for x equal to 0, we have, if we put x equal to 0 in the last equation, we get B equal to D, because A and C vanish here. Thus Ax equal to Cx for all x belonging to V. This implies for x equal to 1 we have a equal to c. Hence the phi image of tau a comma b, which is a, is equal to c, and that is the phi image of tau c comma d. This shows that phi is well defined. Phi is well defined. Next, we want to show that phi is a homomorphism from G into homomorphism between these two groups with G as domain. And for that we will need the result of when we take the product of say tau a comma b and tau c comma d, we get another tau. What we need, what that tau actually is, and this we will just simply write from that thing which we already know about these functions from that previous exercise where we saw these things for the first time. Next, for any, we have already assumed these things, right? We can assume a prime, b prime and c prime, d prime belonging to G. We have phi of tau a prime, b prime composition c prime, d prime, and this composition turns out to be equal to this tau a prime c prime comma b prime c prime plus d prime. So according to the definition of phi, this is a prime c prime, which is nothing but this times this. Thus phi is a homomorphism. Also, for any non-zero real number, any r belonging to G bar, we have tau r comma 0 belonging to G such that its phi image is R, which tells us that phi is onto, it says surjective homomorphism. So in order to show that G by N is isomorphic to G bar, now the only thing left for us to show is that the kernel of this phi is N, is that subgroup N. we now show that k phi according to our standard notation is the kernel of phi. This is equal to n. Let tau a comma b belong to k phi. Then a, which is the phi image of tau a comma b, is the identity element of G bar. G bar is the group of non-zero real numbers under multiplication, so its identity element is the real number 1. So this is equal to 1, and hence, so a becomes 1 excuse me, and hence tau a comma b belongs to n, because n has precisely those type of taus where the first real number, the first subscript is 1. So the kernel of phi is contained in n. The reverse inclusion is obvious. Why? Because an element in n looks like this, tau 1 comma b, which will be mapped by phi onto 1. That is the unit element of the second group G bar. So that's why any such element will automatically belong to the kernel of phi. So the kernel of phi is n. We now have all the pieces. Hence by theorem 271, G by n is isomorphic to G bar. That's what we wanted to show. And this completes the solution. Okay. Then exercise 8. Let G be the dihedral group. Defined as the set of all formal symbols just give me a moment, okay? As the set of all formal symbols x to the power y, I, y to the power j, we have already seen all these things where I can be either 0 or 1 and j can take these n values, where x square is e, y to the power n is e, and x y is y inverse x. Now there are two things we have to prove. two parts. Part A, the subgroup N consisting of all the possible powers of y, integral powers of y. These are all the possible distinct powers of y, because y to the power n is e, is identity. This subgroup is normal in G. Note that this is a subgroup and it is nothing but the cyclic subgroup generated by y, or strictly speaking the cyclic subgroup generated by this formal symbol. Okay, so we have to prove that this subgroup is normal in the dihedral group G. And the second thing is this: B that the quotient G by N is isomorphic to W, where W is the group of these two real numbers 1 and -1 is the group under ordinary multiplication of real numbers. The exercise looks long, but the solution is quite short actually. A. N is normal in G because the index of N in G is 2. Order of G is 2n and order of n is n, so index of n in G is 2, and we already know that any subgroup in a group of index 2 is normal. And in fact, this we have proved in exercise 2 of a previous section 2.6. And G by N is isomorphic to W because any two groups of order 2 are isomorphic. This is a pretty simple fact that any two groups of order 2 are isomorphic, and the isomorphism is given by, say you have two groups E comma A and E comma B of order 2, let's say E prime comma B, to distinguish between the identity elements. Both of them must have one identity element, and since both of them are of order 2, so they must have exactly one non-identity element. You then map the identity element onto the identity element and the non-identity element onto the non-identity element. I leave it to you to verify that such a mapping is going to be an isomorphism of this group onto this. Onto, of course, it's both one-to-one and onto, that we can immediately see, but it's also going to be a homomorphism. So that's why any two groups of order 2 are isomorphic to each other. G by n is a group of order 2, which we can see from here itself. W is also a group of order 2, so they must be isomorphic. That is why. Okay, so this completes the solution. Next, exercise 9. This is also pretty easy. Prove that the center of a group is always a normal subgroup. Solution: let G be any group and Z or Z be its center. Now we have already proved before that the center is a subgroup. That this is a subgroup of G. Now next we have to prove its normality in G. Let G be any element in G and Z be any element in the center, a central element. Then G is Z G inverse. Because Z is in the center, so Z commutes with every element of G. In particular, Z commutes with this small g. So that's why we can write this product as G inverse. And this again belongs to Z. Hence, Z is normal in G. That completes the solution. It's an extremely easy exercise. Next, exercise 10. This one is interesting. It's not exactly easy, but it's not very difficult either. If you try to get the solution, if you try for some time, you will come up with something. Prove that a group of order 9 is abelian. This exercise is actually a special instance of a general result which says that any group of order p square is abelian, where p is a prime number. That, however, we need to see some more things to be able to prove that general result. This, however, can be proved with whatever we already know. Okay, so we start by assuming a group of order 9. So let G be any group of order 9. So the first easy case is this: if G has an element of order 9, it may or may not happen. If this is the case, then G is cyclic and hence automatically abelian. Because then that element will be a generator of G. It will generate a cyclic subgroup of order 9. So that subgroup will be equal to G. Then G is cyclic and hence abelian. Okay, so assume G has no element of order 9. So that is the next case. So that means in that case, every non-identity element of G must have order 3, because you see, the identity element in a group is the only element having order 1, and according to Lagrange's theorem, or rather its corollaries, the order of every element in a finite group should divide the order of the group. So the possible orders are, because the group is of order 9, the possible order of any element is 1 or 3 or 9. If we take a non-identity element, then the order 1 is gone, it's ruled out. And according to our assumption, that element also cannot have order 9, so it must be of order 3. So that's what we are going to write here. Then every non-identity element of G has order 3, and in this regard C corollary, so this is the first corollary, okay, C corollary 1 to Lagrange's theorem. Fine. Now what is the next step? So we are now going to actually choose one such element. Let A be a non-identity element in G. Then the cyclic subgroup generated by A it will be normal in G, and that is something we are claiming. Okay, so we have to write accordingly. We claim that the cyclic subgroup generated by A is normal in G. Suppose it is not. Suppose that is not the case, then there exists an element small g in G such that this GAG inverse is not equal to the cyclic subgroup A, because if this we have equality for every G, then that means the cyclic subgroup is normal. So that the cyclic subgroup not being normal means there is at least one G for which we won't have equality. Since order of GAG inverse is equal to order of A, order of the cyclic subgroup A, which is equal to order of A, and that is equal to 3, and this subgroup has the same order as the cyclic group A, that is coming from a previous exercise. See exercise 4B. Of section 2.5. So since this is the case, we must have order of the intersection of this and the cyclic subgroup. GA, G inverse, should I use another bracket, or we can understand what it means? Intersection A. This is one subgroup and this is the other subgroup. This must be equal to 1. Why though? Let us see. This I am not going to write in detail. I mean, I am not going to make this conclusion. Of course, we have the conclusion and that is a part of the solution, but how the conclusion is reached, I will just show it, but I won't make it a part of the solution. I will rub it off. The thing is this. You see, we have two groups. One of them is GAG inverse and the other one is this cyclic subgroup A. In fact, from this exercise, from part A of this exercise, we know that this is also a subgroup. Okay. Now, So what about their intersection? We know that the intersection itself is a subgroup of both this one and this one. That is, say it's a subgroup of this. We consider only that. So by Lagrange's theorem, the order of this intersection must divide the order of this group, which is 3. So this should divide order of this, which is 3. So that means this must either be equal to 1 or 3, because 3 is a prime. If it happens that this order is equal to 3, say this order is equal to 3, then what does that mean? Since this is already a subset of this cyclic subgroup which has 3 elements, and the subset itself also has 3 elements, so the only possibility is that the subset must be equal to the original set. That is, let me continue the argument on this side. So this will mean that this subset, this intersection, must be equal to this. But this again implies that since this becomes the intersection, so it is itself contained in G inverse. A similar argument with G inverse in place of A will give you this. Okay, because there you will get, if in place of this you have G inverse, then this intersection will be equal to G inverse. That will prove that G inverse is contained in A, and from these two things you will then you will be forced to conclude that this is equal to A, contradicting our assumption. Okay, so that's why this is not a possibility. This intersection cannot have order 3. All these things may look like a bit much to not write them, to not make them a part of the solution, but once you think of it, it becomes very easy. We are just simply going to mention because of Lagrange's theorem. Okay, whenever we mention Lagrange's theorem, you should understand that some sort of division of a group by division of the order of a group by the order of one of its subgroups is involved. Okay, so that's why we are not going to write this. By Lagrange's theorem. So all these things are understood and they are in the background, we are not showing them. So the intersection has order 1, but then what happens? So what is the order of this product of this group, this subgroup and the cyclic group? We have already come across this formula in that section named a counting principle, where we find the order of hk, where h and k are two finite subgroups of a given group. And by that formula, this is times order of the cyclic group A divided by the order of their intersection. And this becomes equal to 3 times 3 divided by 1 equal to 9. So this subset, we don't know whether this product is a subgroup, and we don't need that also. This, after all, it's whatever the case may be, whether this product is or is not a subgroup, it is after all a subset of G, subset of the original group G, and it has the same number of elements as G, so it must be equal to G, which implies G is equal to G inverse A. Okay. Then, so every element in G will belong to this product, and hence will have a particular form. In particular, this element is also here. G inverse is also here. So G inverse will be equal to G a to the power I. G inverse a to the power j. For some integers I and j. Okay, so we have an equation like this. This implies can we say something about G from here? Oh, why have I taken G inverse though? Instead of taking G inverse, I think it will be better to take G, because that will give me something. The element G also is in G, so G itself can be written in this form. Then from this, after cancellation of G from both sides using the left cancellation law and doing similar things, we end up with this. So G inverse becomes equal to or G becomes a to the power I plus j, which clearly belongs to the cyclic group generated by A. But then if that is the case, if G belongs to the cyclic subgroup generated by A, then G inverse must be equal to A, and that is a contradiction. And this contradiction is arising ironically from our supposition that this is not the case. So even in that case, we are getting that this is the case. So our supposition is wrong. Okay, so our supposition is wrong. That is, we must have G inverse is equal to A for every G belonging to G. Thus, this is normal in G. That's what we wanted to show. That was our claim. Our claim has now been established. Now, because this cyclic subgroup is normal, we can form the quotient of G by this subgroup. Now, this quotient is a group of order group of order 3, and hence is abelian. Recall that in a previous exercise we have already proved that any group of order 1, 2, 3, 4 and 5, any such group must be abelian. Non-abelian groups appear only from order 6. S3 is the smallest non-abelian group. Okay, so this is abelian. So by exercise 9A, of section 2.3. Okay, was it this early, this exercise which says that if G by n is abelian, then n must contain the commutator subgroup of G? I am not really sure about this reference. Is it really in section 2.3? This may be wrong. Okay, let me just write the thing and then you will understand what we are doing here. So by this exercise, this contains the commutator subgroup of G. So what we have used here is this. Say G is a group and n is a normal subgroup such that G by n is abelian. Then in an exercise previously, we have proved that if this is abelian, then n contains the commutator subgroup of G. This is what we are using here, but I am not sure about this reference. I may have made a mistake in this section or in the exercise number. If that is the case, you please rectify it. Okay, you understand what we are doing here. Okay, now again we are in a position to use Lagrange's theorem, because this is a group and G prime, which is the commutator subgroup or the derived subgroup of G, that is also a group. So the order of G prime must divide the order of A. Since order of A is 3, Lagrange's theorem implies that the order of G prime must either be 1 or 3. And accordingly, order of G prime is either 1 or 3. That is, G prime is either the trivial group consisting of only the identity element, or G prime is in fact equal to the cyclic subgroup A. Suppose G prime is equal to A. Okay, what happens when that is the case? Choose an element B belonging to G minus G prime. Since G prime is now a group of order 3 and the original group has order 9, so there are elements outside of G prime. 6 elements are there. From them we can choose one element B, and definitely B is not going to be identity, because identity is already there inside G prime. Then B is a non-identity element of G. Now whatever we did with A here, all the arguments, we carried out all the arguments, ultimately we concluded this. We can also carry out similar arguments with B, because B is also a non-identity element, and hence the order of B must also be equal to 3 according to our supposition, our original assumption. And we will get again the conclusion that G prime must also be equal to the cyclic subgroup generated by B. Carrying out all the arguments with A replaced by B, we then get, or we get, G prime equal to B. But then B belongs to G prime, because B must belong to the cyclic subgroup generated by B, and that contradicts the very choice of B. So we cannot have, so we cannot suppose that G prime must be equal to A. It will not be equal to A. So the only possibility is that G prime must be equal to E. Thus, we must have G prime equal to E. This now finally allows us to show that G is abelian. Let us see how. Let X and Y be any two elements in G. Then this element xy, let me write it here, xy, x inverse, y inverse is in G prime, because G prime is the subgroup of G generated by such elements. So such elements in particular are also in G prime, which has only the identity element, and hence x, y, x inverse, y inverse must be equal to the identity. This implies, if you look at the equation carefully, this implies xy has to be equal to yx. Therefore, G is abelian. The general result which says that any group of order p square is abelian where p is a prime, it can be proved in a much easier manner once we have the tools. This one is somewhat long because we now know of only a few things. We have only a few things at our disposal to use. So we have used whatever we want in any way possible, and we have got the solution, at least in this case. That is when the prime is 3. Any group of order 3 square is abelian. Okay, so after this, exercise 11. Let G be, if G is a non-abelian group of order 6, prove that G is isomorphic to the group S3, the symmetric group of degree 3. So up to isomorphism, there is only one non-abelian group of order 6, that is S3. That's why we sometimes say the non-abelian group of order 6. And its solution is already available in the text, although in a section that is yet to come, but still we do not want to repeat the things here. So we are just simply going to, ideally we should struggle with it. We should struggle to show that it is the case with whatever we have up to this point. That is the purpose of this exercise, but we can sometimes also leave results. Leave results means leave exercises or take the help of something advanced from a section that is yet to come, so that we don't get stuck somewhere completely. Okay, so we are going to write, see the third application at the end of section 2.9. So we have some time before we get to this point. In section 2.9, I think we have that thing known as another counting principle. I think it's that. I can't remember exactly. Then exercise 12. There we have some application of a result where the third application contains this thing. If G is abelian and N is any subgroup of G, prove that G by N is abelian. Since G is abelian, N is normal in G, and that is why the quotient group G by N makes sense. I need ink. So let us take two elements in G by N and show that they commute. Let N G1 and N G2 be two elements in G by N. But since G is abelian, G1, G2 is the same as G2, G1, and hence we have this. thus G by N is abelian. Then exercise 13. Let G be the dihedral group defined in exercise 8. Find the center of G. And we have already found it in a previous solution. So we refer to that. C see the solution to exercise 17 of section 2.6. In that solution we have actually found the center of G, the dihedral group, and since the dihedral group has, we should not say the dihedral group but a dihedral group, we can say the dihedral group of order 2n. Okay, that we can say. Since it depends on n, recall that in a previous exercise we have shown that the center is trivial when n is odd, and the center is, I think, this when n is even. Okay, this particular element besides the identity commutes with every element of the dihedral group when n is even. In the actual exercise where we did this, we were just simply asked to show that the center is non-trivial when n is even, but we in fact found the entire center. We showed that this is the center. Okay, so we can refer to the solution to this exercise, and there the center has been determined completely. So with this, let us end this video. We have, after this, how many exercises? 17, 18, 19. I think up to exercise 22 or 23. I can't remember exactly. So we will see the other exercises in the next part, next video. So until then, it's me, Lucifer, from a mathematical room. Have a nice night.